again, this isn't a quiz. On the other hand, we are going to have one tomorrow, so keep that in mind. It's on the calendar. It's been sitting there. But again, all I'm looking for is, can you tell me the acceleration of this system? And assume that static friction has been broken so that it's sliding. Seems like some of you are going to get the wrong answer because of what I just saw in your paper. So let's correct a few things here. There are two forces acting on the hanging block, correct? And we know one of them is going to be tension. But the pulley is a heavy pulley. So one of the first things you're going to have to do is recognize that there's two different tensions on either side of the pulley. So not all of you did that, but we'll say this is tension on the right, and there'll be a tension here on the left. So you can differentiate the two tensions. Oh, I gotta check your ID. All right, I think we'll be okay. I got a little collection of these going. Colton's, Sacketh, they're all right here. Sacketh, thank you. How else am I supposed to know? There's nothing wrong with that. The real question is, tomorrow morning when I say it wrong again, will you correct me a second time? That's good. It's the only way we learn. And I'm stubborn and old. And that makes it really tough. All right, so going back to this, two different tensions. A few of you still had the same tension, but the pulley doesn't turn unless there's two different tensions. So we have four forces acting on this box. We'll have tension to the left, weight downwards, normal force upwards, and a frictional force to the right. It should not take you long to figure out how you're going to express your frictional force, right? Just a couple quick substitutions. So when we look at the forces acting on this box, I think we'll have TL minus mu times 2mg equals 2ma. Any questions about those choices? Because I saw a few people making just little mistakes, like not putting the 2m for the mass here, stuff like that. I know it's all little, but it all starts to add up. The one that's hanging, we're going to have mg and tr. I'm going to make, if it's not obvious, I'm making this direction the positive direction. So we'll have mg minus tr equals ma. And now the pulley. And most of you did fine on the pulley, so I was pretty happy to see that. We'll have RTR minus RTL equals, it's a disk, so 1/2 2m r squared. And I think we can probably blow past that and say that the motion of the pulley is directly connected to the motion of the blocks. And if you can get all three of these, you're going to get the answer. So are there any questions about where any of these came from? Go ahead. We're calculating torque. So this is actually the torque on the pulley that's causing it to spin to the right, and this is the torque on the pulley that's causing it to spin to the left. So in calculating the torque, it's still the torque arm length times the size of the force times the size of the angle. But for any pulley, we can leave the angle out because the string's always going to wrap around the pulley until it comes off as a tangent. So that's always going to be a sine of 90 degrees. Is that a sufficient answer? All right. Go ahead.
So since torque is radius times force, why do we only include the tension one, not the frictional force?
The frictional force is acting only on the block on the table. The pulley is spinning. So if there's friction on the pulley, it'd be in the bearing of the pulley, somewhere like here, where it's mounted. So unless it's specified that there's friction in the bearing of the pulley, we can assume that the pulley itself isn't experiencing friction because it's just spinning. Is that okay?
Because it's not friction from the blocks. We're talking about from the pulley itself. The forces acting on it.
Yes, we're talking about the forces acting on the pulley itself. Something to consider, we haven't actually addressed the fact that there are four forces acting on the pulley. And if we were asked about the pulley, like what force does the mount apply to the pulley, can you identify the four forces that act on the pulley? I think two of them are obvious, but maybe the other two less so. So if I have the pulley here, there's two tensions that act on the pulley. There's also going to be gravity acting on the pulley, but it's mounted to the table somehow. I don't show that, but there's probably a force this way from the table on the pulley to keep the pulley from going someplace, right? The pulley's mounted in some way. So we're not talking specifically about that, but there's no reason that you shouldn't consider those forces in the system. But these should all be zero, right? If your pulley's staying in place and just spinning, you would expect the net force on the pulley to be zero, but the net torque not to be. All okay? All right, so going back here, the rest of this problem is largely algebra. So we're going to put these things together and work out the acceleration. We can reduce this problem by getting rid of all the r's. And I don't want to become too complacent with this, but I do want to say one thing about this. Right now, these problems are kind of basic, but the whole point is to kind of get you start working on how these problems kind of come together. You should notice in these problems that it is the pulley that ties everything together. That's where all the two internal forces are listed. We're not doing substitution because we are adding these equations together, but if you were asked to find an individual tension in the string, you would probably have to do substitution. So keep in mind that the only reason all this cancels out is because we're eventually just looking for the acceleration. But one of the things I want to point out here is that at the end of the day, you should get something with a friction problem that looks like this. Now, this again is me trying to make sure we emphasize that this is still Newton's second law, with this portion being the net force acting on the system and this being the inertia and the acceleration. So again, the effectiveness of your forces in order to cause an acceleration. The question that often comes up is the object speeding up or slowing down? That's here. Anytime you're faced with a problem that has a subtraction, your answer can be positive or negative. So pay attention to those threshold questions, meaning there's a threshold here. If this is bigger than this, the system is slowing down. But if this is bigger than this, then the system is speeding up. Understand how to answer that kind of question from looking at a relationship like this. So the threshold, the point where they are neither speeding up or slowing down, is when the net force equals zero, when those two things are equal. Good? All right. This next question is going to be harder. We're going to move away from the Atwood questions. You have two other Atwood questions in your homework. You should look at them. There's no point in me going over it with you until you've grappled with them. The most we will do a lab on is the ribbon question. We're going to do the lab next week, but this question is one that it's been on the AP exam. It's in every single textbook that there ever is. The idea is if you wrapped a ribbon around the outside of a disc and released it, what would be the acceleration of this system downwards? We're not going to work it out today until you've given it a shot, but I feel confident that if I gave this to you as a quiz tomorrow, a lot of you would have trouble with it. So before we go any further, 2 minutes, can you work out what the forces would be acting on this system? Problem is quite literally just deciding where to begin on it. But there are only two forces that act on the system. Here's the hint. This problem can be done two different ways. One of them is actually easier than the other, even if it doesn't feel that way. The first way to do this problem is probably the way you're envisioning it, in that there's a pivot point here, and it's rotating about its middle. So many of you will probably do the problem that way, and that way works just fine. Everything that you would normally do is going to be okay. mg minus t equals ma. That's going to be true. Those are the only two forces acting. They're both acting up and down. It's a one-dimensional problem. It's the net torque side that you're going to need to be careful with. However, I would encourage you to consider doing this problem from its actual pivot point, because it's not pivoting about the middle. It's actually pivoting here. That's the actual pivot point, because that point is at rest relative to the toilet paper roll. It's rolling. And anything that rolls is actually pivoting about the point of contact. It doesn't appear that way because the moment it rolls to the next position, it's in a new point of contact. But that's the actual pivot point, because that point is at rest with respect to the environment. The middle is not at rest. The middle of this toilet paper roll is moving downwards. In fact, it's never at rest. But this point is at rest, and it's actually pivoting there. However, if you want to use that, you will have to use the parallel axis theorem to shift the moment of inertia to the edge of the disk. Try this problem at home. It's a classic problem. We've laid out most of it, but I would really like to spend some time on a much more difficult problem. Okay? This is the problem I'd like to think about today, because what I really want to talk a little bit about today is rolling. And rolling is a condition. So to speak about rolling, I want to talk about the conditions for rolling. And trust me, there are some real challenges in our future when it comes to some of the kinds of questions that we can answer now that we know things about torque. But rolling is a condition. And if you're told something is rolling, you are being told that the point of contact is at rest with respect to the object and the surface. It's also known as rolling without slipping. When you are told that something is rolling, they are giving you a piece of information. It's not obvious, but they are giving you a piece of information. If you're told that something is rolling, then this will be true for the object. And this will be true for the object. And this will be true for the object. Our pulleys and such had strings that are going around the outside of them, but things that are rolling are spinning and moving with translational motion at the same time. The Atwood machine questions we did, the thing that was spinning stayed in place, and the net force on that thing was 0. But for systems that are rolling, this is something that you have to consider, because there is the possibility that you could have this condition. They'll call it rolling with slipping. This is not truly rolling, but they might say that it's rolling while slipping or with slippage. And what this means is that it's actually not rolling. Rolling's a condition. So if you have something that's slipping, then none of these are true. I'm not going to rewrite them all. I'm just going to write one and say none of these are true. Meaning the rate that it's moving translationally isn't matched up with its rotation. When you were a kid, you probably skidded your bike once in a while, locking up the back wheel and sliding. But what's truthfully happening is if you are rolling with slippage or the wheel is slipping, that means there is kinetic friction acting on your object because it is moving with respect to the surface. So if you're rolling with slipping, you have kinetic friction. But if you're rolling without slipping, you have static friction. It does not take much friction to cause something to roll. However, dealing with friction for something that's rolling can be a head scratcher for the first few times you've seen it. So I want to talk about this question specifically and how we address it. I want to find out the size of the frictional force acting on the disk. So we have a ramp with an angle theta, and I'm asking specifically to figure out friction, and I'm telling you right now, you can't have mu in your answer, because if it's rolling, then we know that static friction is on a sliding scale. It's an inequality, and you are probably nowhere near the threshold. So if you're asked to figure out the size of the frictional force for something that is rolling, you're going to be putting this in terms of the angle and the mass and those particular variables that you've been given. Something about the shape will probably play a role in this too. So what I want you to do is I want you to consider, before we do anything else, what are the forces acting on the disc or ball or whatever it is, and what direction do they point? Meaning, draw them as they act on the object, where they act on the object. And think critically about each one of them. There's only 3 forces. I'm going to assume you got the easy ones, right? You got the normal force and you got the weight. Did you draw those? So I assume we have an arrow downwards for the weight. And did you draw the normal force from the point of contact through the center and upwards? It would go through the center because the normal force is perpendicular to the surface and therefore is going to go along a radius. That's important. How did you draw your friction? Did you draw it up the ramp or down the ramp? Friction in this situation will be up the ramp. If you're trying to figure out the direction of friction, friction is what's causing this to roll. It's causing that point to stay in contact. So when you're trying to figure it out, because it's not always going to be easy to figure out the direction of friction for something that's rolling, it's what's causing the rotational rate to change. So consider the ball here. Would you agree that it's probably going to be accelerating down the ramp? Does that make reasonable sense? That it's going to get faster and faster as it rolls down the ramp? That means its spin rate is going to get faster and faster as it rolls down the ramp. So the frictional force has to point in the direction that's going to cause the system to increase its rotational rate. So I know some of you probably had friction drawn in the wrong direction because I saw you do some erasing, but whenever you're asked this question, that's how you have to handle it. And it won't always be easy. So now that you know that, let's talk about how you might go about solving this problem. You have 2 choices to make. You have to choose where your pivot point's going to be. And you have 2 places you could pick to choose to, you have 2 places you could choose to put your pivot point. You can put your pivot point at the center and trace the object as it rolls down, assuming you're watching the center of the object. Or you can put your pivot point at the point of contact. As I said to you a minute ago, it's actually pivoting about the point of contact. So if you want to use the true pivot point, you should use the point of contact. But you can use the center. It's just 2 different ways to do the problem. So in this class, I'm going to do the version that you guys vote for, and then whatever one you guys don't vote for, I'm going to do the opposite version in second period. So vote. Do you want it at the center or do you want it at the edge? So who votes for the center? Who votes for the edge? Then we're doing the edge in this class. So we'll place the pivot point here, and we're going to work the problem from here. Now, before you go any further than this, this is still the same problem as we had first semester with an object on an incline. So your net force equations are still all true. So start with your net force equations. So I'm not going to spend a lot of time reviewing that. You should kind of have a handle on it by now. mg sine theta down the ramp minus friction up the ramp equals ma. None of that's different. That still has to be true. Newton's laws still work here. We just don't know the size of the frictional force. We can't substitute in mu times the normal force. It is also true that normal force minus mg cosine theta is equal to 0. That is also true. I don't know how helpful it's going to be, but that's also a true statement. So these are our force equations. We'll tuck them over there. Let's talk about torque now. There are 3 forces acting on your system. Which one is causing a torque? Is friction causing a torque? It can't. It's acting at the pivot point. So if we chose this as our pivot point, friction is not causing a torque. Is a normal force causing a torque? Can't. It's acting at the pivot point. When you place the pivot point where you placed it, and I let you vote, the only force that's acting at a distance, some distance away from the pivot point is gravity. So gravity is actually causing the torque. Friction is keeping that point of contact from slipping, but gravity is causing the torque. It's gravity that causes it to roll. We tend to think it's friction, but friction just holds the point of contact still. So we're going to have to deal with this particular torque. Our torque arm distance is r, the radius of the disc, right? It's from the edge to the center. That's where gravity's acting. The size of the force acting on it is mg, right? That's the size of the force acting due to gravity. And there's an angle right here. What angle do you think that is? Yeah, it's got to be the angle of the ramp, right? Because if there's no ramp, it'd be 0. But if there is a ramp, then it's whatever the angle of the ramp is. So theta has to be that angle. And because this is a torque, and we would normally put the sine of the angle between the torque arm and the force, this will be the sine of theta. This is the only thing causing a torque. So this has to equal I alpha. I said that this was a solid ball. Have you memorized your moments of inertia yet? I didn't say you had to memorize them, but if you know them, it's going to be easier. If you don't, you have to look it up in a table. So go ahead, look it up in a table. You have to. I've memorized it. It's a solid sphere. It's 2/5 mr squared. You might want to consider just knowing the fractions for all the round things. It's not hard. 2/5, 2/3, 1/2, and 1. And I would have them in order too, from easiest to turn to hardest to turn. A solid sphere is the easiest to turn. It has the most mass near the center. Followed by the disk, then the hollow ball, and then the ring. That's the order from easiest to turn to hardest to turn. The problem is that that's the moment of inertia about the center of mass, 2/5 mr squared. But we're not pivoting it about the center of mass. We're pivoting it about the edge. So we will have to use the parallel axis theorem. So we take the center of mass, 2/5 mr squared, and we shift it. How far are we shifting the axis? R, yeah, 1 radius, right? We're going from the center to the edge. So we're shifting it by mr squared. Any question where I got any of those values from? Okay. If we add these together, you get 7/5 mr squared. All right, just got common denominators. Now we can put this all together in our torque equation. It's a green one though, so it can't be an emergency. If it's an emergency from the green office, they come get you. So we're good. Or if the officer comes get you, that's usually an emergency. Haven't had the officer show up to pull a student out in a long time, but it could happen today. But if the officer shows up here wanting a student, that's usually not pleasant. It's been fun to watch though. Yeah, as a teacher, no, they'll take him. That's great. Do you want his backpack too? Oh yeah, they'll want your backpack. Oh yeah. They'll probably want your phone too. They'll make you go get that. Actually, they'll just probably go get it for you and ask you what number it's in. It hasn't happened in a long time, so we're probably all good. All right, so we're gonna pull it all together. So RMG sine theta equals all of that. And I think because it's rolling, I can go ahead and make this substitution. Right? Rolling guarantees that that substitution can be made. I don't even have to question it. Now, again, just like before, you're going to notice that all the R's cancel here. That's not accidental. This is the way this stuff works. But do you see all the R's canceling out? Now, that would not be true if you had some kind of weird situation. There are weird situations. This is not one of them. So this R cancels, these R's all cancel, and I'm left with mg sine theta equals 7/5 ma. Do you remember what was being asked in this question? The size of the frictional force, which means between this relationship and this relationship, we want to eliminate A. That's our goal. So I think we can do so pretty easily. First, I'm going to notice I have that 7/5 ma there. Do you guys see it? So one of the first things I would do is write this as 5/7 mg sine theta equals ma. By doing that, this can be substituted in for ma. I think that's probably the fastest way to do this substitution. I know you could solve for a, but I think it's better to solve for ma. Do you guys see that okay? I know I'm going a little fast, but I think we'd want to see a conclusion. So I'm going to go ahead and do the substitution here, and we're going to get mg sine theta minus friction equals 5/7 mg sine theta. Now, this part's not too crazy. We just want to solve this for friction. So I'm going to just do a little bit of algebra, subtract this from both sides, noting it's less than 1, and get 2/7 mg sine theta, and then move friction to the other side. Now, this is a challenging bit of work the first time. There's a lot here. Again, in second period, we're going to do it from the standpoint of the middle of the ball. And I'll make sure I use a solid sphere there as well, just so you can see it if you're interested. But please pay attention to the following few things I want to say. This is the required amount of friction to make this roll. It is based on several qualities, and they don't show up here, but they're there. The harder something is to roll, the more friction that will be required to make it roll. So we chose a ball, but if you put in a disc with the same mass, it will be different. You'll get a different answer because it requires more friction to roll than the ball does. So this represents the minimum amount of friction for your object to roll. It is still subject to this condition. So you may not have enough friction to make something roll. This is what's required. This is what you have to work with. So when you're looking at a problem like this, you could be asked, is there enough friction to make your object roll? You would have to find this part out first, and then test it and see if there's enough friction. But remember, you can't jump to using static friction because it's an inequality. Because of that, you don't know how much friction it's actually going to take. The only way is to look at the conditions of the problem. And please look at the parameters here. Obviously, if it's more massive, it takes more friction. That's not a surprise, because if it's more massive, it's going to be harder to turn, harder to roll, harder to move. All of that's going to still be true. But please notice that the moment of inertia ends up being wrapped up in here someplace. Right? That's where it worked out to be. So somehow that 2/5 mr squared got wrapped up inside of this somewhere. Obviously, the angle makes a difference too. And please notice that the angle plays an interesting role here. So it takes more friction to get something to roll as that angle changes. You guys know how sine works, right? So it takes no friction for something to roll on level ground. Friction is not required just to have it rolling, right? Sine would be 0 degrees, and the sine of 0 is 0. But it takes more and more friction as you make your thing more steep, because it's going to accelerate faster and faster. because it's going to accelerate faster, you will need something to turn it faster. That takes more friction. So we're going to stop right here because I think the bell rings in like 30 seconds. Is that right?